today we're going to talk about, Caleb, what we call the inclined plane. That's a fancy word for ground at an angle, a flat plane, a level plane. That's what we've been doing so far. What if we put them on an incline? We're going to start with a couple of little thought experiments. And I deliberately led off with the one before class, and I'm glad Kyle came up with his 0, because we're going to use a similar strategy. For me to answer these, I'm going to try to go to the extremes. If I'm not sure what the correct answer is, I'll say, well, what if it's really big or really small? Okay, so here's what it says. Suppose a person is standing on a ramp, standing on a Newton scale, so instead of the scale reading kilograms, it reads newtons, but it is a bathroom scale, so what is the scale measuring? Okay, so really this question is talking about normal force. As the angle of the ramp increases, what happens to the scale reading? Or, in physics speak, as theta gets bigger, what happens to Fm? Increases, decreases, or stays the same? So we have them attached by a rope. They're standing on a scale. As this angle gets bigger and bigger and bigger, what happens to the normal force? I'm going to go to the extremes for angle theta. And my extremes for angle theta, what's the smallest angle I can be in degrees? 0 flat. And what's the biggest angle I can be? I'm going to then assume that whatever happens at 0 and whatever happens at 90, the transition is smooth and just doesn't magically jump around and not follow any math rules. So if theta was 0 degrees, how big is the normal force exactly? mg. Now imagine it got steeper and steeper and steeper. In fact, imagine if it was 90 degrees. Wouldn't you actually be dangling from the rope? So if theta was 90 degrees, how big is the normal force if you're dangling from the rope? No, all of the force is tension, but the normal force is nothing. So it goes from mg, which is maximum, to 0 as theta increases. So here's my question. Did the normal force increase, decrease, or was there no change? Decreased. I used the same strategy I brought out earlier. When in doubt, for thetas, go to the extremes, 0 and 90 degrees. If I need to, I may even bring in 180 degrees if I need to, but those are my go-to. You okay with that? And there's my proof. I should probably make this a bit more organized. Theta equals 0 degrees, comma. Therefore, Fn equals mg. Theta equals 90 degrees, comma. Therefore, Fn equals 0 newtons. Therefore, decreases. This isn't a beautiful proof because I have a bit of English. The word decreases, but it's pretty close. What that means is, as soon as we're on a ramp, can we simply assume, oh, but look, and the normal force is mg? No, because apparently it gets smaller as the ramp gets steeper. Same question. What happens to the tension in the rope? I'm going to do exactly the same argument. I'm going to say, all right, what if theta is 0 degrees? And what if theta is 90 degrees? If theta was 0 degrees, wouldn't the rope actually be kind of hanging slack? What would tension be at 0 degrees? Braden, what about at 90 degrees? What would tension equal exactly? Imagine it. Imagine the free body diagram. Do it in your head. He's not accelerating. So what happens to tension? Okay, now that's if a rope is holding you up. If it's not the rope holding you on the ramp, if it's your own shoes, say you're standing on a roof, that would be friction. Turns out friction has to get bigger to hold you up as theta gets bigger, which again makes sense. You can easily stand on a hill that's not very slanty, but if you're on a really, really steep hill, you start to feel like you're going to slip because friction isn't big enough to hold you in place. The real question is, how can we come up with actual numbers? And Ange, I've given you a bit of a hint. We're going to use angles as the job for components. Did I say angles? Components. Really the question is, what are the best components? I'm going to say to you, vertical and horizontal are not the best this time. We're going to use a different reference frame. If we look at a ramp, gravity is the main force. So if I said to you, what are the forces acting on this block sitting on the ramp? Get the obvious one. All of you right now, draw a big MG. Nice and big, please. Not small. And then, ready? I'm going to tell you one more trick, and you'll see why later. Always put the MG on the pointy side of the triangle, which in this case is on the right. If the pointy part was to the left, I'd put MG on the left. If you don't, MG shows up in the middle of your components, and it gets confusing because you don't know where MG belongs anymore. Trust me, I've done this before. Here's what I'm going to argue. Gravity is doing two things. Part of gravity, don't write this down, is pulling this down the hill. Part of gravity, don't write this down, is squeezing it into the hill. And this is going to be how we're going to break this up. This you can write down. I'm going to zoom in to make it nice and big so you can see how we're going to do this. We're going to break up gravity into components. Because the rest of the forces, Caleb, are either going to be in line with the hill or perpendicular to the hill. So rather than change all of those other forces to make them match gravity, it's much easier to take gravity and componentize it. How? We're going to break it up into a perpendicular component. And this one is going to be at right angles to the surface. And a parallel component. And the parallel component, Lena, that is supposed to be exactly parallel to the hill. The perpendicular component, and I did a lousy drawing, is supposed to be, wow, that's even worse, is supposed to be exactly 90 degrees perpendicular to the hill. Put arrows on the end, so put an arrow pointing perpendicularly down and perpendicularly parallel. Because now you can see, Mina, I did add those together tip to tail, so I've done the vector math correct. MG, sorry? Mitra. I can't believe I did that. It's been a long time. Mitra, my joy, MG is the hypotenuse. Okay. The real question is, how can I find an angle? Because if I can find an angle and I have the hypotenuse, I can use trig and I can find the components. Okay? Now, ready? I did the components as red dotted lines because the blue line is the force, but I broke it up into components. There is one other force acting on this. Is this block sinking into the ramp? Is it flying into the air like Superman? So there is a normal force, but look, the normal force by definition is at right angles to the ramp. So the normal force will look like that. And it'll be at a nice right angle. And do you notice I drew it exactly the same length as the perpendicular component of gravity? That's what the normal force is. It's no longer mg, it's going to be the right-angled component of mg. That's what the normal force is. And that parallel component, don't write this down, that right there, Lyndon, that's what's pulling this object down the ramp. That's what's causing it to slide. If this ramp was really flat, almost dead level, that parallel component would be really tiny, not enough to cause it to slide down the ramp if there's any sort of friction. So here's what I wrote. In terms of the other forces acting on the ramp, there will still be the normal force, which by definition is perpendicular to a surface. If the surface is rough, there would be friction. So if we say here mu equals 0.45, then friction would be pointing up the ramp because this object wants to slide down the ramp. This is going to be a frequent free body diagram. So it says this, example 3. Draw a force diagram for an object on a rough ramp that is sliding down the ramp. Okay. Ready? By the way, right here it looks like it's digging in. I just couldn't get the block to line up properly. So imagine it's nice and smooth and sitting on the ramp. What are the forces acting on this block? Get the obvious one. And that's still going to be straight down. And I'm going to put the mg on the same side as the pointy part of the triangle. Now, that mg is the one that we're going to break into components, and it's going to break into a perpendicular component and the parallel component with a lovely right angle right there. Sarah, is this block sinking to the ground like quicksand? Is it flying to you like Superman? So there's going to be a normal force, and the normal force is at right angles. And I'm going to tell you right now, it's going to be the same size as the perpendicular component of gravity. That's what's creating the normal force. That's the Newton's third law. Forces come in pairs. That's the pair. Which way is this block sliding? So which way is friction pointing? I got to be fussy. Down the... Yeah, in other words, not down the ramp. I got to be fussy now, because down might mean straight down. Down the ramp. So which way is friction pointing? In the opposite direction of motion, which is going to be... 3 words, up the... Yeah, that's what I want. Okay? So we can put friction this way. Don't write this down. If this is bigger than the parallel component, it won't slide. If friction is smaller than the parallel component, it'll accelerate down the hill, but not very fast. If friction is really small, it'll accelerate down the hill a little faster. We could also be sliding up the ramp. How would that work, Mr. Dewick? Something gave it a big push and it kept going for a while. What are the forces acting on this? Get the obvious one. Yep. What else? Oh, let's break this up into components. Mr. Duck, yeah, Eric. Why do you always draw the perpendicular first and then the parallel? Because that's going to allow us to memorize one approach and notice where theta ends up every time. You don't have to draw perpendicular first. I always will. You could do this. That's legal. I find that kind of yucky. So, what else? At right angles to the surface. Caleb, which way is this block sliding?
Up the ramp.
So which way will friction be pointing?
Down the ramp.
And so this time, unlike the previous one, you actually have 2 forces down the ramp. You have this one and you have this component. What that means is if you try pushing something up a ramp, it'll stop really fast as compared to this example where it might still continue sliding down the ramp. This is how we're going to use components. We're going to use parallel and perpendicular. So, example 4. Turn the page. Which of the following is the best free body diagram for a mass that is at rest? You know what? We should underline or highlight the word at rest, because that's the key to doing this question. On a ramp. If it's at rest, what's its acceleration? What's the net force? Same answer. So all my forces are, in physics 11 I would have said, I'm looking for a word that begins letter B. Balance. Okay. The tricky part to realize is never let gravity stay the way it is. We're going to break gravity into components. So if I break gravity into components for the right hand for diagram B, I get that. Sarah, do you notice in diagram B, I have a force down the ramp? Do I have any force up the ramp? Then this would have to be accelerating down the ramp, Newton's first. Could this possibly be at rest? Now, take a look at diagram A. If I break gravity up into its components, here is my tie right there. That's a net force of 0. And here is my tie right there. That's a net force of 0. What's the net force overall? 0. Will this accelerate? That one works. Explain your answer using principles of physics. I did with a good free body diagram. That would convince me. Is that okay, Karen? My friend who created this handout, he talks about the squeeze and the slide components. The squeeze component is what causes the normal force. It's, what is it, upside down capital T a symbol for? Put a little upside down capital T right there. And then for the slide components, put two slanty lines side by side. Upside down capital T is the abbreviation for perpendicular. Right angled 90 degrees. Two slanty side-by-side lines is the abbreviation for parallel. 1R, double L, 1L. I'm going to use those as my abbreviations. Okay? We're going to do a proof because the angle that you're always going to get is the angle of the hill, and we need to find a way using that angle to figure out where it's going to end up in our component triangle. We're going to do a proof once, and then we're just going to memorize it. So, in order to determine the size of the squeeze perpendicular and slide parallel components, we need to find the angle in the coordinate triangle, complete the proof below to show that the angle is always equal to the ramp angle. Huh? All right. This vertical one here, gravity. Don't label it, but that's where it comes from. How big is angle number 1? Look at it. Now, don't write this down. I'm really going to muck this up. That triangle there, if theta was 30, how big is angle 2? 60. If theta was 31, how big is angle 2? If theta was 40, how big is angle 2? So what you're telling me, angle 2 and theta have to add to 90, because all triangles add to 180. So if I want to generalize this, angle 2 is theta minus 90. If theta is 50, angle 2 is 40. If theta is 1, angle 2 is 89 degrees. Be a dumb one, but okay. Yep. 90 minus theta. Thank you, Nate. Good gosh. Candy for you later. Now you folks are at a disadvantage because you haven't had much geometry. There's a little bit of geometry in Foundations of Math 11. When I taught Foundations of Math 11, I did a lot of geometry because geometry is pretty cool. It's the art of proofs, and I like to try and prove things and do good arguments. What you would learn, we're going to have to be clever. So we would normally say this. Don't write this down. How big is this angle? How big is that angle? How big is that angle? Okay. How big is that angle? It's the same size as angle 2. It's the same size as angle 2. Now, how could I prove that? In geometry, in the old curriculum, you had learned that any time there was a letter Z, like that, the two inside angles were identical. We called them alternate interior angles. Some kids called them zangles because you were always looking for a Z, but you couldn't use that on a test. We used to have to do actual proofs on the old Math 12 provincial exam. So, without going into a lot of detail, I'm going to tell you that angle 3 is equal to angle 2. Symbol for angle is like a capital L that's been stepped on. Well, the symbol for angle is an angle, right? Which means angle 3 is 90 minus theta. So how big is angle 4? Can anybody see it? What? Caleb. What we're going to do from now on, Caleb, is this. We're going to color that there. We're going to color the top angle there. In other words, on the previous one, right here, I would do that and that. I would do that and that. Those two angles are the same. If you always draw perpendicular first and then parallel. And that's why we're always just going to draw our diagrams the same way, Ange. Okay? We've done the proof once. We're not going to do it again. Candy for Nate, candy for Caleb.
Where's candy?
Maybe it's the green headband. Taking out the number, but that's harder. So that part is worth memorizing, although you'll do these so often, Lena, you'll naturally memorize it. But if you come to me in a week and say, I can't remember where the angle goes, I'm going to probably damage your self-esteem a little bit because it means you haven't done any of the homework. Let's do some with some numbers. Here we go. Example 6 says, find the acceleration of a 2 kilogram mass sliding down a frictionless 25-degree angle ramp. Okay. What do they want us to find, Spencer? Okay, and the acceleration is going to be in that direction, so we're rarely going to ask you specifically for a direction because the direction is going to depend on what angle theta is. We're going to just want the magnitude. Okay. You know what this is a job for? So, rather than redraw this, here in particular, if they give me the ramp, I will label the diagram itself. What are the forces acting on this 2? Get the obvious one. Folks, draw gravity nice and big. In fact, I often draw it so that it crosses that bottom line because it gives me another 90-degree little reference that I might find coming in handy. What side is the pointy part of the ramp on? Right side or left side? Put the MG on this side, trust me. Before I do the normal force, I'm going to break gravity into components. I'm going to break it up into, but now I'm going to label it. That's the perpendicular part. I'm going to label it as mg perpendicular. mg with an upside down capital T as a subscript. And then I'm going to draw in this one. And I'm going to call this mg parallel, using the 2 lines for parallel. Spencer, is this block sinking into the ramp like quicksand? Is it flying off the ramp like Superman? So the forces into the ramp must be canceled out. That's the perpendicular. There's a normal force, and I'm going to eyeball it. I'm going to draw it just as big as mg perpendicular. Those two are a Newton's third law pair. Is there friction? If there was, friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force, and an 8 mg. Okay. Spencer? 25. 25. Color that. Which way is this block accelerating? And don't say the word up or down. I want a 3-word phrase with the word the in the middle and a word ramp at the end. Down the ramp. And I got to be fussy now, Sarah. Up and down no longer cuts it. Okay? I'm going to ask you again, Spencer, not to make fun of you, but we're going to go on a little dance here. Which way is accelerating? Which way is the winning direction? What's the winning force? Don't say mg. Mg parallel. Who's winning? Mg parallel. Who's losing? Losing would be anything pointing up the ramp. Is there anything pointing up the ramp? No loser. What does winner minus loser always equal? Real question is, what the heck is G parallel? Time for some trig. That mg, which is the one that I know, opposite, adjacent, or hypotenuse. Little h there. Mg parallel. Which trig function? What always goes next to the trig function? The angle. What's the angle in this case? Equals. Don't get your calculator out yet, please. Patience, young grasshopper. What over what? Psst. Yes? Yes? Let's get the G parallel by itself. Nope, sorry. Equals G sine. I'll just put the theta there as a generalized one, in this case 25, but there's our generalized, and I'm not going to memorize it, but I'm going to give you a clever way to memorize it. What's G parallel the same as? G sine theta. What's G parallel the same as? G what theta? G what theta? Which trig function? Which trig function? Which trig function? Which trig function? Are you telling me that G with two lines is sines? That will always work if you always draw the triangle the same way I'm showing you, which is perpendicular first and then parallel. That will not work if you start doing your own thing. But if you're looking for a stupid way to do this, G, two lines, is sine. Anybody want to guess what perpendicular is? Of course you know the answer. Okay. So here's what I actually see. I drop the M down, but instead of G parallel, I'm going to write G sine theta equals MA. I also noticed something else here that's kind of cool. What happens to the M's? Is there an M in everything on the left? Yeah. Is there an M in everything on the right? What happens to the M's? How many of you have gone skiing before? Okay. So let's imagine perfect snow, not snow with friction, snow that has no friction. Okay. That's what we have here. We have a ski hill with no friction. This explains why a little kid and a grown-up can ski side by side. If the mass didn't cancel, the grown-up would have to constantly be adjusting their skis to stay with the kid, which they don't have to. The M cancels. That's if there's absolutely no friction. Okay. And if there's a little bit of friction, okay, you got to do it. And that's assuming the kids and the grown-ups have the same skiing ability, so that the kid's not snow plowing or introducing extra forces or anything like that. But there, I don't know if you've ever wondered why that's the case, but that's the case. The M cancels. What does this want me to find? Let's plug in numbers now and go. So A equals, what's G? And not negative. We decided in this case to let down be positive because it was mathematically way more convenient. 9.8 sine and theta is actually 25. By the way, there's a built-in error check. If you were in free fall, if the ramp was 90 degrees, what's the maximum acceleration you could have? Are you in free fall? It's going to be less than 9.8. Okay. By the way, what if the ramp was a full 90 degrees? What if theta was 90? Well, now you'd be falling off a cliff, yes? Can you go 9.8 times the sine of 90? What do you get? What do you get? Turns out the sine of 90 is 1, and it has to be 1, otherwise our physics wouldn't work. What if you were flat? What if there was no hill? First of all, what would your acceleration be as kind of a Captain Obvious? Nothing. What's the sine of 0 degrees? Is it 0? Does it actually give us no acceleration? So the trig that you're learning in Math 12 and some of the cast rule stuff that you did last year, it has to be that way. Otherwise, physics doesn't work either. Nate's having a little mind-blown moment there. Oh, example 6, too easy. No friction, too easy. I do like example 7. I do like example 7. I do like example 7. Okay? Now, if I give you a question with friction, and I will, I also need to tell you which way the mass is moving or trying to move. Because if it's trying to move down, friction is going to be pointing up the ramp. Sorry. If it's trying to move down the ramp, friction will be pointing up the ramp. If it's sliding up the ramp because someone gave it a push, friction will be pointing down the ramp. A says, find the force of friction on the mass. B says, find the acceleration. Lyndon, you know what this is going to be a good job for? Before that, you know what this is going to be a good job for? Absolutely. Absolutely. Lyndon, what are the forces acting on this 5? Get the obvious one. Now, the other reason I'm telling you to draw mg big, don't write this down. Every year, I see a kid who does this, and then they go components. And do you notice it isn't obvious which theta looks correct? Where if I draw it nice and big, label that mg. There's mg perpendicular. There's mg parallel. I'm going to argue that if you draw a big triangle, it's kind of more obvious that the 35 has to be the top one because the top one does actually look smaller to the naked eye as opposed to if you draw a little tiny triangle, you can't tell. So I typically draw my mg until I'm touching the bottom of the ramp, or I might even go further. Nate, color in the 35. Lyndon, color in the 35 here. Color in the 35 up there. And I encourage you, put the 90 in, because that helps you figure out that mg is the hypotenuse. You with me so far, Nate? I did it again. Nate sits here in my other block. Lyndon? Wrong block. Yes? Okay. What else? So we've taken gravity, we've componentized it, we're not done. We have a normal force. How big? It's going to be the same size as the perpendicular components. I'm going to eyeball it. By the way, don't draw the normal force like that. It's always at right angles to the surface, at right angles to the ramp. So it'll match the perpendicular component, and mine ends up being about that long. Ish. I might be a bit longer, a bit short. If I gave you the free body diagram to draw as a test question, and I will give you a free body diagram to draw as a written test question, I would take marks off if you did this, or if you did this. Okay. Now, if you're close, I'll be okay with that. I think last time I went past the. This time I stopped right before the. Close. What else? Is there friction in this question? Yeah, it says mu is 0.2. Which way? Which way is this mass sliding? Friction is always the opposite direction of motion. I'm pretty sure friction is shorter than mg parallel because these are the two, these are the two, these are the two, don't write that down, that are having the tug of war. It's those two. And since it says it's sliding down, I'm going to guess that mg parallel is winning. Now, if it said sliding down but slowing down, friction's winning. What does A want me to find? Friction is what times what? Let's write that down. I don't know the normal force. Oh, but look. I do know another force the same size as the normal force. And it ain't mg! Which is by far the most common mistake kids make, which is why I tried to beat that out of you last year already. What's the same size as the normal force based on my free body diagram? Mg perpendicular. So you're telling me friction is mu mg perpendicular. Let's do the trig. Hypotenuse adjacent. Which trig function? Lyndon, my friend. Of course it is. So, you ready? Parallel, that one, which is opposite, which is another dumb way to remember. It's sine, 2 lines is sine. The adjacent one, perpendicular, the one that isn't 2 lines is sine. Of course it is. You can also derive it. I've showed you how to derive it. So we could say cos, let's go general, theta equals mg perpendicular over mg. Lyndon, the m's would cancel. To get the perpendicular by itself, you would times the g over, and you'll get g perpendicular equals g cos theta. Lena, you can derive it if you wish. This might, by the way, might be a couple of nice ones to add to your blue formula sheet as part of your study guide if you wish. You can't put it on your yellow sheet. I've given you dumb ways to remember if you want to do it that way. You use it often enough that typically the kids memorize it during this unit because you get sick of trying to derive it all the time. So if I hear you correctly, Lyndon, you're telling me this. Friction is going to be mu mg cos theta if I want to generalize. Now let's be specific. Hey, Lyndon, what's mu? I don't know. What's mu with you? What's mu? Good. What's the mass of this object?
5.
G, 9.8, not negative. We took care of that. Cos, and what's theta? 35?
Yeah.
How many newtons is friction? I get 8.03. Anybody else? Newtons. I have to be honest, I don't often specifically ask you to find the force of friction. I typically jump straight to find the acceleration, which means you're going to need to do friction in your acceleration equation anyways. So, Lyndon, let's keep going. Which way is this thing accelerating? Thank you for saying it correctly. Which way is it accelerating? You're right. So what direction will the winning force be pointing? Who's winning? Mg parallel. Who's losing? What does winner minus loser always equal? Yep. Now, we could drop that 8.03 right into the friction equation. I'm going to do this algebraically for a reason, because something kind of nerdily cool is going to happen. So, you ready? This would be mg parallel minus mu times the normal force equals ma. You would say, I don't know the normal force. Oh, but look. And you would go mg parallel minus mu mg perpendicular equals ma. Braden, did you notice something kind of cool? Is there an m in everything? So in this one, so even if there is some friction on a ski hill, can a grown-up ski with a little kid without having to constantly adjust due to the mass imbalance? Yep. Now, if they are adjusting, it's because the little kid can't ski as well as the grown-up or vice versa. But it's nothing to do with, oh my goodness. Now, The grown-up is also physically larger. There's more air resistance, so we're ignoring that. So I guess I'm fibbing a little bit. I'm not being completely 100% accurate, but reasonably. Okay. What am I trying to find? I need to get the A byte. Oh! This is why I did it this way. Is it turns out if the M's cancel, you've already got the A by itself. When will the M's cancel? If there's an M in every term. If one of those terms had not had an M in it, don't be canceling. G parallel. G2 lines. G parallel. G2 lines. 2 lines is sine, you say. Oh. So you're saying this is G sine theta minus mu. Which trig function was perpendicular? It wasn't sine. Of course it wasn't. Was it cos? If you want a general equation for an object sliding down a hill with friction pointing up a hill, I guess there it is, because I didn't use any numbers. That's all variables. Oh, and that would work on the moon with a different G or on Mars with a different G, but now let's plug in numbers. 9.8 sine 35 minus 0.2. 9.8 cos 35. Am I in free fall? So I know it's less than 9.8. If you got an answer bigger, you've messed up. 9.8. Try typing this in. Sine 35. Where's your calculator? Yeah, get it out. Okay. Type. Minus 0.2 times 9.8 cos 35. 4.02. That's how we'll break ramps into components. By the way, we could have, Eric, taken the normal force and broken that into a vertical component, and taken friction and broken that into a vertical component. Rather than changing two forces, it's much easier to muck around with gravity. Also, because gravity isn't going to change, it's always going to be the same thing. It gives us an identical approach we can use every time. You okay with that? Not too bad. This is just easy enough to be tough. And what I mean by that is most of you are going to get good at this. Most of you are going to lose so many marks to mistakes. What are classic mistakes? Caleb, I've lost track of the number of times. In fact, I did it. You see it? Because I'd already written a G in my mind. When I wrote that first G, my brain had checked off that I'd written a G. They forget to write the G there. Now, I caught myself in the calculation, at least. That happens all the time. Or they forget the mu. That happens all the time. Or one of the G's they forget to put a trig function next to. That happens all the time. Because I would argue, Lena, really not that difficult. The tricky part was wrapping your brain around what reference frame the components would work best for. But now it's sine and cos, which I'm going to suggest we did last unit quite a bit. And it's not that different from horizontal and vertical components from last unit, except, okay, 2 lines, parallel is sine, and of course it is perpendicular. Example 7. I like it, or example mystery. I like example mystery. I like example mystery. I like example mystery. Example mystery is a nice question. Although it's a little too easy. Really? Yep. A block remains motionless. I would probably underline the word motionless on a surface that is inclined at an angle of 21 degrees. What's the minimum coefficient of friction on the surface? What's this question asking me to find? Hey, what's mu? I don't know. What's mu? How will I start this before I even do anything else? What am I going to do? Dolp. Yeah. Can't do this in my head. Except, can I change it? It shouldn't be dolp. It should be dab. Draw a biggish picture. So, I'm not, again, I've lost track of how many times I see kids draw that, and then they got the block, and then they're trying to... Well, of course they're going to get the triangle wrong. So I left you like a whole half page, yeah?
Yeah.
You could have your triangle pointing to the left. When in doubt, my habit is to the right. 21 degrees right there. Block. Right there. You can put the 7.5 kilograms on the block if you want to. I often don't because it's in the question and my block gets cluttered with the free body diagram anyhow. Okay. Cool. Matt, what are the forces acting on this block? Get the obvious one. Which way? Straight down? No, straight down. Just straight down. Gravity hasn't changed. You notice I drew it biggish, and I always label the MG on the same side as the pointy part because that way it doesn't end up inside my triangle and confuse me. Before I go further, since we're on an angle, I'm going to break gravity into components. I'm going to break it up into perpendicular and parallel. By the way, do you see how I'm able to figure out how long to make perpendicular? If I made it this long, there's no way that parallel would work. That's not parallel to the ramp. Or if I made it really short, so you're eyeballing it, you're stopping when you know that that line there will be parallel to the ramp. Try and be reasonably accurate with your free body diagram. It helps. What else? Is there friction in this question? Real question is, which way? Well, with this stuff... Oh, I'm missing a normal force. I should have done that first. And normal force is going to be the same size as the perpendicular component. Caleb, what was that? Why must it be up the ramp? Because nothing's canceling out the parallel. If this would, by the way, this would be a ramp made of perfect ice. That's your free body diagram. The two blue forces are the actual forces. The red dotted lines actually wouldn't show up on your free body diagram. They'd show up when you broke it into components. And if there's friction, not only that, who's winning? It's a trick question. Because it's motionless. So how long should I draw friction? If I eyeball it, the same length as parallel. Not longer and not shorter. Lots of information there. Who's winning? It's a trick question. It's a tie. So what equation can I write? What equals what? There it is. The rest is going to be plugging away in substitution. So friction is what times what, Matt? Mu times the... I don't know the normal force. Oh, but look. I know another force the same size as the normal force, and it's not mg. Is there an m in everything? Well, that's kind of cool. So, Mr. Dewick, are you saying that the mass is irrelevant in this question? Yeah. Whether it's a 10 kilogram block or a 1 kilogram block, same coefficient of friction. Oh, G parallel. Sorry, G perpendicular, not G parallel. G perpendicular. Which trig function? G... Was it cos? Again, common mistake. Kids, because they're so hyped on the angle part, they write the cos theta, but they forget to drop the G down. Equals whoa Braden, what happens here? Munir, what? Is there a G in everything on the left? Is there a G in everything?
this hasn't happened before. Well, first of all, let's keep going. How to get the mu by itself, because that's what it wants, the coefficient of friction. Have you all learned yet that sine over cos is actually tangent in disguise? Okay, you'll learn that have you done trig identities? Really, that's what I should have asked.
No.
You'll do those in Math 12. Later on this year, you'll actually learn that tangent is also, among many other things, sine divided by cosine. You can try it on your calculator. If you go sine of 30 divided by cos of 30, you'll get the same decimal as tan of 30. Anyways, for what it's worth, if you had done Math 12 already, I would say, ooh, cool, this is tangent. But for now, sine 21 divided by cos 21. What's mu? Yeah, you all can all try typing tan 21. I'll do sine 21 divided by cos 21, and we get exactly the same thing, 0.38386, that there. I'll go 0.384. 0.384 what units? Oh, nothing. Matt, let's go back here. What the heck does that mean? So once in a while, you will come to such a universal equation that G cancels, and what that's telling you, Sarah, is this would work on any planet. Okay? So if you had Star Trek technology and you beamed this directly to the moon, the block would still be at rest on the moon. Or if you beamed it to Mars, the block would still be at rest on Mars. If you beamed it to Jupiter, if Jupiter had a surface, it's a gas giant, so it doesn't technically, but if it did, the block would still be at rest there too. It's irrelevant. The gravitational field plays no role. It's kind of cool. Later on this year, we'll actually do a roller coaster where that happens, and we'll have realized that we've just designed a universal cosmic roller coaster that would work anywhere in the universe, which, on the nerd scale of things, I have to admit, Matt, is kind of nerdily cool. Preview of coming attractions. Is example 8 my last one? Okay. I'm going to give you part of the homework now. When do I see you next? We'll mark the take-home quiz. That'll take a while. I'll finish off this lesson. I'll give you a lot more of the homework because this is the Physics 12e stuff. But for now, you can do number 1. Now, when it says and write force equations, I'm not fussy on that. I've been teaching you actually from the free body diagram to be able to go straight to solving. So, free body diagram, sure. But cross out A, just do B. Find the acceleration. You'll have to do a free body diagram and come up with the equations anyhow. What's A ask you to find? Yeah, what's VI in this question?
0.
What's D in this question? 12. Now that I have the acceleration, VI and D, could I also find time for part B? Yes. All of the unit 1 stuff. Could I also find V final? Yes. So now we can start to calculate speeds at the bottom of ramps. How long it takes you to get to the bottom. All you need is the acceleration, and then solve physics 11. Okay, so 3 is a good one. 4 is a good one. 5 is a good one. Okay, I'll assign the rest later on. Now, honestly, I suspect you'll have a fair bit of time on Monday to work on the homework, but I'll finish off the lesson. I will be assigning a whole bunch of these because you need some practice, but there's your head start, okay? Do I have a cool